So, welcome everyone. I'd say we slowly start. I'm Roland Wolters. I'm Technical Marketing Engineer for Isovalent, and I'm happy to welcome today Philip Nikolic, who is the architect owner of Kubernetes, of the Kubernetes environment at PostFinance. And he's here today to talk us through PostFinance Cloud Native journey, especially how PostFinance uses Cilium, Hubble, and Timescape to simplify their network and also prepare for scale. So, and with these words, I immediately hand over to Philippe. But before I do this, don't forget for everyone, if you want to ask questions, feel free to. I will try to answer them during the presentation already, and we will also have a Q&A session at the end. So also use the Q&A section. We'll try to provide answers, and there will be enough time at the end to discuss whatever you have on your mind. Thank you very much. Philip?
Thanks so much, Roland. So, as already introduced, I'm the architect owner at PostFinance, one of Switzerland's largest financial institutes. And just to give you a couple of numbers in order to really understand what this means, we do have quite a lot of customer assets. So, obviously, our customer assets are mainly in Swiss francs, which would be turned around into about 115 billion US dollars. We have 2.6 million users. Switzerland is not that big of a country with a huge amount of population. So this actually is quite big if you look at it percentage-wise. And 1.9 million out of those use an online system quite frequently, which we call our e-finance system. Each and every year, we do have to make sure that 1.3 billion transactions go through our network, which would calculate up to about 3.5 million transactions a day. And this obviously are just the pure bank transactions that we do from one account to the other. So as you can imagine, there is a lot more things going on with the evolution of how banks make money. And also when it comes to trading certain issues and whatever it is. So we really do have quite a lot of transactions going and passing through our network all the time. So how exactly do we handle those kind of issues? There is quite a couple of those. And just to mention a few, you may think this looks a little bit familiar to you. If it does, we try to have something similar to the CNCF landscape for our own internal products that we're using in order to manage this amount of transactions and this amount of user satisfaction that we're going through. And as you can also see, we do use certain CNCF tools, talking about OpenTelemetry, Jaeger, Kubernetes, Argo CD, and so on and so forth. And today we're specifically going to talk about Cilium. So why did we choose Cilium in the first place to begin with? Well, we do have quite a lot of Kubernetes environments. By this, I simply mean we do have over a dozen of clusters, and they all need to be provided with networking. And so, as many of you may already know, there is a CNI for this, so a container networking interface, which you simply install basically as a plugin into your Kubernetes environment, and this one will handle all things related to networking inside the cluster for you. So it will assign IP addresses to your services, it will assign IP addresses to your pods, and so on and so forth, and forward all the packages to the respective things. Many of those CNIs, however, do base upon IP tables one way or another. This is mainly due to the fact that Kubernetes was built with an application running inside of it called kube-proxy that runs on every single node, as the daemon said. And if you have kube-proxy, you're eventually using by default IP tables. There's also a more modernized version. However, IP tables has a lot of issues when it comes to scaling. Mainly those issues being that the more you fill up your tables, your IP tables, which essentially is just a firewall and says what traffic is allowed to pass through and which isn't, the more you fill it up, the slower it will get. So it doesn't really scale in a good amount. With that, we really had to start thinking, is there some kind of way that we can eliminate iptables, that we can eliminate kube-proxy? And this is exactly where Cilium came into place. And we made a case study together with the folks from Isovalent, which you are free to check out. It's publicly available. And as you can see here, this is a benchmark that we did with our system before we switched to Cilium and after. As you can see, outgoing connections, there may not be that big of a difference. However, if you add up those milliseconds, those about 30 milliseconds onto many, many scenarios that could potentially come up because pods start so often, this may actually become a huge deal for you. And especially if you then look at the connections to a Kubernetes service, because all of those things need to be created with rules inside of iptables. And this takes time. It takes a lot of time to process and to be able to distribute across all those nodes. And even longer, it did take us to connect from one pod to the IP of another pod. This took us in our tests up to really 60 seconds, up to 1 minute. Someone had potentially to wait after deploying a pod in order to do this. With Cilium, as you can see, we're not just talking about maybe doubling it or just ×5. No, it's actually really an X 1000 factor that we see here compared to 5 milliseconds, 60 seconds that we see as a maximum value for those networking issues. And so for us, it was clear that Cilium is exactly what we want to stick with. And over time, the ecosystem of Cilium evolved as well. And so we looked at what is there else? Is there something Cilium related that we could use and that will also give us huge benefits? And so we came across Hubble. Hubble is an open source project. You can find it on GitHub. And it helps you observe the current traffic flow inside of your cluster. Okay. So it gives you a CLI and a graphical user interface for you to be able to see and recognize what is actually going on inside of your cluster. Not what you think it is doing, but really showing you what it is doing. It provides you with a big variety of filtering mechanisms that essentially give you exactly what you need to do whenever you need to do it. On the right-hand side, you can see an example of how the Hubble UI is looking like. Here you can see that in a namespace called My Application, I do have a front-end and a back-end application, both of them on TCP port 80. And over our ingress, Nginx, we're calling the front-end, which makes a call to the back-end. And it's really as easy as this. And depending on what you would see here, one can investigate further. So what exactly did we use Hubble for? What kind of problems did it solve for us? Well, not only were we able to debug much faster and see also with our application developers that what they think they are doing, the kind of network calls that they think they are doing aren't really those that they were doing. But also we were able to inspect some very technical deeper to do some very technical deeper investigations regarding package drops. Now, I want to quickly give you an idea of what package drops are, because this really is an issue that we came across quite often in our environments due to our own libraries and also open source libraries that were used at the time. And essentially a package drop is when Cilium stops forwarding your packages. To many of you, this may seem like a Cilium issue. However, although it can be, most of the time it isn't. It's an applicational issue. It simply suggests that something doesn't work as intended. And whenever something doesn't work as intended, you usually want to alert on it when it occurs. And so for those reasons, there is a metric inside of Cilium called Cilium_drop_count_total, which you can have an alert set on, and it's going to alert you whenever those drops occur and also give you a reason why those occur. There's multiple causes that can lead to package drops. There's a lot of causes. For example, it could be an unsupported protocol. However, the two most likely ones are that the destination is unknown or that there is a network policy dropping it. For both reasons, obviously, Cilium rightfully is going to stop forwarding your packages. If you give it a destination address which doesn't exist, which isn't inside of your cluster, which is nowhere to be linked to, Cilium cannot forward it and therefore will drop it. In the same way, if you have network policies that shall drop packages from one namespace to another or outgoing connections, Cilium is going to do this in its right way. And this can be alerted to, which also helps to figure out if perhaps an attacker is inside of your cluster and tries to do some kind of weird service discovery and find out what that person can do. And with your network policies, as long as you have them in place and have an alert on them, you can find out that something is doing something they aren't supposed to do. So to give you an idea of one of those scenarios, I really want to quickly go through DNS lookup inside of Kubernetes. So if we do have application A simply deployed as a pod and a cluster IP service, which also gets an IP address. Usually, in order for application A to communicate with application B, this would go through this service. And so whenever you call the service, you would actually receive from the DNS inside the cluster, the DNS, the IP address of the cluster IP service. So in this particular case, application A is doing DNS lookup of the service, of the cluster IP service, and would get back the IP address with 50.50. How exactly does this look like if we were really to try it out? Well, as you can see here, I do have a service called application-b. It's of type cluster IP, and the IP address is 50.50. If I now look at the pods inside there, there is exactly 3 pods running: application B, and application B, all of them with a different IP address. However, if I do an NS lookup on the service itself, I am only seeing the IP address of that service being 50.50. I do not have any idea how many pods there are behind the service, and I do not have any idea of those IP addresses. So this is how a cluster IP service works. However, there is a very special kind of cluster IP service, which doesn't have an IP. This special kind of service is called a headless service, and oftentimes used especially for distributed computing if you have some kind of discovery, some kind of service discovery that you have to do, and where you need to be aware of all the pods that are running behind the service. Just imagine you, for example, having a database or some other thing that needs to know about all of its members in order to be able to vote for something, to be able to do a quorum of something. This is how one could do this using service discovery and a headless service. In this case here, application A, again, is going to do a DNS request for that one particular headless service. However, since this service does not have an IP address by itself, it's going to return all of the IP addresses of the pods behind it. So again, to show it really how it looks like, this time we can see at kubectl get service that we do have a service called headless. It is of type cluster IP. However, it does not have a cluster IP. One can argue that the name therefore isn't really fitting. However, it's just a special case of cluster IP service. We can also see that we do have 3 pods running, and all of them with a different IP address: 0.200, 0.201, and 0.202. If we now inside of an application try to look up the service headless, we will see that we will actually really get 3 IP addresses back. We'll get .200, .201, and .202. And so by doing this, we now know, hey, there is 3 other pods running behind that service. And sometimes weird things happen when you do this kind of service discovery. So what exactly can happen now? We established that application A now knows exactly the IP addresses of all the pods behind it. And now it can communicate with them directly. One could also go over the service. However, since we do round-robin load balancing over the service, you cannot really be sure that you really did communicate to each one of them exactly once. If you make 3 calls to the service, it could happen just by a chance that you will not have done one request to the first pod, then to the second, and then to the third pod. It could just so happen that instead all 3 would go to the same pod all the time. And this is where the service discovery comes in. So now I do have the knowledge that 3 pods exist, and I do know the IP addresses of those 3 pods. And so now I can go ahead and call them. Question is, what happens now if I do cache the IP address .200 and the pod having the IP address .200 is being killed for whatever reason? Kubernetes having a deployment or stateful set or any kind of replication in there is going to automatically make another pod being created. However, the IP address changes. It's not going to be static since we're in a containerized world where everything is very, very fast-paced. And so if my application now is continuing to try and do those calls to the IP address .200, this exact call is being dropped by Cilium. It may be a huge pain in order to investigate how this is exactly happening. However, this is where Hubble comes in and really helps you, and you can see why your calls do not work in the way you would have expected them to go. So with the CLI tool of Hubble, what one can do is simply do a Hubble observe. As I mentioned already before, it has a very good filtering mechanism. And by that, I mean that with Hubble observe, we can now have -- from namespace and really say what namespace we want to look at. There's nothing worse than an incident happening and you have too many errors to look for. So really being able to filter those, even at huge scale, even when you have 100 or 1,000 of namespaces running, each with maybe 100 pods in there, is really helpful and necessary in a big environment. And so we can simplify our search and say, hey, I want to look for the namespace Hubble -demo. The -f simply means follow. So if I don't do this, it's going to give me a one-time output. If I do -f, my terminal is simply going to stick in there and really show me all connections that are going to happen in there. As you can see, I can already very easily in the first line see what's going on. I can see application A on an ephemeral port 5526 is sending some kind of data to application B on port 80. And it's being forwarded, and I can also see the TCP flags being sent, since it is trying to connect to it for the very first time. And so it is going the normal TCP flow, send, SYNAC, ACK, so on. Then we're going to push some data, and at the end, also finish it. Down there, however, you can see what happens if this particular case is then going on, where now a pod has been restarted. After the break of the new line, you can see that application A on port 608086 is going to reach out to the pod with the IP address ending on .200. We're all the time sending those sends. However, they will never reach it because it doesn't exist anymore. And you can see there right before the TCP flags that this package is being dropped. So in order to go further, even further, if you have your alerts in place and you're now being alerted that there is drops happening, how exactly can you see just the drops and not all the other mess that's going on? Because there will still be oftentimes also things that go through. So for that reason, we do have another very useful filter. It's the exact same command, Hubble observe from namespace Hubble demo, but this time with a -t option. This -t option now takes in what kind of type we're looking for. Do we want stuff that is being forwarded or packages that are being dropped? And so here, immediately, we can see exactly what's going on. We can see that there is an issue with application A. For some weird reason, application A is trying to reach out to a pod IP. This may seem very weird to a lot of application developers, especially if on a high level. Usually nobody bothers with really calling IP addresses. And oftentimes it's not really the fault of an application developer. It is actually the fault of a library that is being imported that does networking for you. Sometimes, unfortunately, those libraries do a one-time lookup and then cache the IP address. And so until the lifetime of the pod application A, this is not going to change. It is always going to make a call to the IP address .200 because this one was the IP address that it discovered in the very beginning when it started. So this is what we can do with Hubble. However, there's a couple of limitations that even with Hubble, we cannot do. Its biggest strength is also its biggest limitation. Hubble is exactly there for us to be able to observe the current traffic. But this now opens a list of questions. What about flaky issues? For example, flaky in the way as flaky tests. Issues that do come up in the middle of the night, and by the time tomorrow morning you're at work and you're able to investigate the issue, it doesn't occur anymore. What happens to that? So it raised the question, really, how are you able to inspect traffic from the past? And can you somehow, in some way, store traffic, the traffic flow somewhere, and retrieve it later on for debugging and analysis purposes? So in order to overcome those limitations, there is a tool called Timescape. Timescape is a tool really involved heavily with Hubble, and it has a seamless integration with it. And so it allows you to query traffic from the past, exactly what we would like to do. The traffic flow is being exported to a bucket, to a simple S3 bucket, or any kind of bucket that you can imagine that's compatible with it, for example, MinIO as well, and then ingested into a ClickHouse-DB, which is there in order to make analysis, in order to be able to make SQL statements towards it. So to give you an architectural understanding of how Timescape works, this is it. At the very top, we're seeing multiple clusters, cluster 1, cluster 2, and so on. Each of them running Cilium, Hubble, and so on. We can configure Hubble to export our data. Our data can then be exported into a bucket, and somewhere else, we're going to now have a ClickHouse-DB run. This ClickHouse-DB, in front of it, has the so-called Timescape ingester. It's a microservice. All it's going to do is connect to that one bucket, check if there is new data in there, and if so, it's going to ingest it inside of the ClickHouse-DB. Now we also need somehow of a possibility and to be able to query those data sets that are inside of the ClickHouseDB. To do that, we do have the Timescape server. It is practically there for you to connect to it and then to be able to not write your own queries, but instead go ahead and simply use the normal Hubble UI or the normal Hubble CLI. And the Timescape server is in the background going to write the SQL statements for you and format them in a nice output for you. So I'm going to go ahead now and give you a small overview of how this UI looks like exactly. As you can see here, I'm using Cilium Enterprise. This, however, is going to look very, very similar, even if you just use the open source version of Hubble. And so what you can do here is, as you can see, I have a local cluster available right now, and there is a couple of namespaces. All of them are namespaces. And in here, I can click on one of those namespaces. And immediately, I can see what application are running inside of it. I can see application A is connecting to application B on TCP port 80. And as I can see down here, I can also see that there is quite a lot of flows and they have decreased a little bit over time. Up here, I had about 500, 800 flows, and then reducing them to about 70, 80, 90, 20, and so on. So I do have here a similar timeline that I would perhaps know from tools such as Grafana, Splunk, whatever it is that you're using, Elasticsearch, doesn't matter. And so it now helps me to investigate what's going on. Usually with Hubble, starting out in a live view. The live view is going to show me exactly what is going on right now. This is only being used by Hubble alone without Timescape. In here, I can see that application A is talking to application B on port 80, and it's being forwarded. This B flag is in. You can also see the timestamp here. However, there seems as if there is no further connection going on. That's not really correct. This simply looks like one connection being established and nothing else, because I am aggregating those flows. This simply means that it is not going to show me each and every package that goes through this. If I uncheck this box, we can see that there is indeed quite a lot of packages going through. And now I can see them in further detail if I have to do some analysis of TCP, perhaps, if I have to really look at all the packages necessary. Going back with aggregate flows, I will just see one connection being there, because that's what's important. There is nothing really much changing. I can also have some other filters, since probably every application needs to connect to a DNS inside of our cluster as well. Hubble is smart enough to recognize this and not show it up to us. If we want to, however, it would basically look as if there was many DNS requests all the time to it. So what happens now? Let's say a couple of hours ago, I got an alert. It was in the middle of the night and it wasn't a production issue, so nobody was looking up anything at that particular time. But I found out that due to the alert, there were some drops. What I can do instead is close my live view, which makes me being able to now query in the past between a certain time frame that I want. And in here, I can now choose a verdict, forwarded or dropped. In my particular case, if I put away the aggregate flows again, I see all of those flows, and most of them are forwarded, as you can see. If I click on dropped, I will now see that exactly between the time where an alert was made, where the alert was triggered, that application A is trying to send something to this particular IP address. I can now go ahead and further analyze application A, do whatever is necessary in there, dive deeper into the application itself, possible libraries, and so on that I have to do. There's also a nice visualization for more things if you were to connect them together with Cilium network policies as well. You can see a lot of things here. You can see, for example, what connection a microservice is doing. You can see exactly when it did happen and how the flow is. Especially useful if you have to debug quite often certain critical applications. However, the application developer isn't there to give you an insight on how those microservices really play together. And so looking at the live view, we can also see that, for example, there is a service called Crawler that is connecting to the Twitter API. And so depending on how much of the Cilium ecosystem you want to use, you will be able to see more or less in here. However, at all times, the least you will see is exactly what you need, which is what application is calling another application. To also give you an example on how you could use Timescape or the CLI. For this, you would have to do a port forward. You would have to do a port forward onto Hubble Relay. If I go inside of the Cube system, I can see here that we do have a pod called Hubble Relay. In order to use Hubble as a CLI tool, we somehow need to be able to connect it. A very easy approach to do so would be to make a port forward to this particular pod here. We do this on port 4250, port 2. This, now we will be able to use Hubble. And here we can also see certain configuration that we may or may not have, and also set exactly what kind of port and so on we want to connect to. In my case, this should actually be, I believe, 4250. This is the standard port with which Hubble should work automatically. So if I now do a Hubble observe -f here, pardon again, it is 4245, 4245. Port forward, and now using Hubble, I'm able to see all kind of traffic that is going on inside of a cluster. And this is a lot. This is a lot. In order to not see the current traffic, what I can do is do a Hubble observe, and then, for example, just look at one namespace that I want to, for example, drops, and I can look at everything within the last 10 minutes, for example. So I'm going to make those queries automatically to Timescape. And what I'm seeing here with the timestamps as well is that those calls really go up until a very big amount of data. So with that being said, this is how the UI works and the CLI. And going on with what else we're planning to do on, there is a couple of things for the future to go through. So in the future, we also want to extend all of this that we're using. Pardon, my presentation is going off the records here. And so what I truly just want to say for the very end is that we do plan on evolving our PostFinance Cilium environment even more and more. It would be very nice if we were able to provide our application developers insight to the Hubble UI. However, due to compliance reasons, this is not really possible. As a financial institute, we have to guarantee that people only see what they're supposed to see. Giving someone access to the Hubble UI is essentially granting them access over all the network flows inside the entire cluster. For that reason, Hubble RBAC has been developed, which can give you the access over OIDC and ensure compliance guidelines are met. And so teams will only be able to see their own traffic in a multi-tenancy environment, as it is oftentimes the case. To add on this, we also have a couple of other points that we want to establish into PostFinance in the future, as well being ingress controllers, since it is a layer 4 and layer 7 ingress controller. And so oftentimes a limitation of many solutions out there of an ingress controller is that they do only support HTTP. This may be an issue if you want to run something like Kafka inside of your cluster, which really needs to be able to have those raw TCP packages sent inside of it. However, the ingress controller right now requires a service of type load balancer, which is also a little bit difficult since we are not in a cloud environment and would therefore have to on-premise build a solution upon something like MetalB perhaps. So this is currently some of the points that we also are looking forward for in the future and want to see how this develops. Thanks so much. If it's now time, I would say, are there any questions, Roland?
Yes. So first and foremost, thanks for the presentation and thanks for all the details and the insight. That's really great. There are a couple of questions. Let's go through them. Let's start on this side. So first one, can the bucket or ClickHouse DB be reused across multiple clusters? Very good one.
Okay, that's a very good question. So as of right now, I did also have that use case. And so I talked to some of the developers at Isovalent about this. Our idea would be to also be able to have the ClickHouse DB perhaps outside of the cluster and to reuse it over multiple clusters. As of right now, it needs to be a 1-to-1 ratio. So inside of each cluster, you would usually have your own ClickHouse DB. However, this is a milestone right now on a roadmap. And so within the future, this is going to be an exciting feature that I'm looking forward to. And then it will be able to have really just one ClickHouse DB, one huge ClickHouse DB for all of your clusters. You're going to send in all the data from that one bucket, and you'll be able to query them as expected.
Yeah, that would be nice to have this kind of observability with cluster mesh then at that time. So looking forward to this. Second question, can one use Hubble without Timescape? Well,
Hubble without Timescape? Yes, totally. You can think of it basically as Hubble being an add-on that you can have in your Kubernetes cluster that runs on Cilium. Recently, they also developed it that far that you do not even have to run Cilium on it. And then Timescape is another add-on for Hubble. So you can really decide on your own whether you do want to have a Kubernetes cluster with Cilium, and then if you want to just have Hubble, if all you need is the current traffic flow, you're free to do so. Nobody's going to tell you otherwise. And if you want to go then one step further, at some point in time, you can use Timescape as well.
Great, thanks. Next one, I'll probably take that one. It's, does Timescape cost something? Well, it's part of our enterprise offering, so there is costs with it. If you're interested in the prices and everything, feel free to reach out to us on isovalent.com. Also, if you want to have a look at the enterprise features we are offering as part of the enterprise offering or the enterprise product, check out isovalent.com/product. And there you also see a feature matrix listing all the different features which are in the open source version or as part of the enterprise version. Next question, and this is from Chris. Hi, Chris. It appears the traffic bypasses the head end after being assigned a pod. How long does the session take to fail over in that instant? I assume the traffic needs to reconnect to the head end to be assigned to a new pod? Question mark.
Okay, so let me please read through this a little bit again.
Looking here,
It was a
Philip
longer
can.
question. So it appears the traffic bypasses the head end after being assigned a pod. How long does the session take to fail over in that instant? Assume the traffic needs to reconnect to the head end to be assigned a new pod. Okay, I'm not really entirely sure what you mean by a head end. Do you mean the headless service, perhaps, or what is it exactly going to do? Essentially, if you mean the one slide, which I'm going to share with you again, just to be on the same side here, we can talk about this one perhaps. A headless service really similar to a cluster IP service is, if you call it directly, just going to distribute it to one of the pods. However, you will never know which one. So the actual idea of a headless service is that you use it for service discovery and not really as sort of a load balancing tool. So what you would do is instead is just one time make a DNS query to it and then receive all the IP addresses of the pod behind it. After that, you can on your own decide which pod you're going to talk to. So in that particular sense, it doesn't really bypass the headless. It's more that your application A is not even going to call the headless anymore. It's only doing so for the initial DNS lookup. I hope this answers the question.
I hope so as well. And Chris confirmed that was exactly the slide he had in mind when he wrote the question. So, and David, are you planning to use latest Cilium features like service mesh or native ingress?
Yes, so as I mentioned, the native ingress is really something that we want to use. Unfortunately, since we're on-premise right now, we do have this limitation of it currently only supporting services of type load balancer, which on-premise is not working in exactly the same way. However, service mesh is really something that we're looking inside of the company for quite some time now already. There is a lot of promising features inside of the service mesh of Cilium. Right now, however, the one pain point that there simply is that we want a service mesh that we can also use for non-Kubernetes things. We really want to be able to connect with everything, also with our legacy applications, which is a little bit hard to do. Cilium is, to my knowledge, currently the only solution that goes into that direction of having a Cilium agent being able to run on a VM outside of the cluster. Being able to do this, you can then connect it to your VXLAN that you have inside of Kubernetes, and it's going to do all the necessary routing, and you will be able to establish secure connections everywhere and be able also to perhaps do network policies and so on. However, it is still not an easy task to do this, to engineer this. And so it's going to take some time until for an enterprise this really is onto that level. But we're looking at it very regularly and evaluating it honestly quite sometimes very often in the year.
Great. Thanks for the answer. So much for the answers. I'd quickly like to highlight one thing in case you're wondering where to go next after this presentation. So there are a couple of things you can do, or we invite you to do. First and foremost, as Philip has mentioned, there is a PostFinance case study. You can find it on our webpage on isovalent.com/resources. There is also a short link mentioned here where you can download the PDF and go through it. It was also just posted to the chat. In case you want to get your hands dirty, kind of, or want to get some hands-on experience with Isovalent, with Isovalent Cilium Enterprise, feel free to join our Isovalent B tracks. These are guided hands-on labs covering different topics around Cilium, Hubble, eBPF, and so on. If you want to check them out, you will also find them on isovalent.com/events. I think they're monthly or bi-monthly. You can sign up for them, and then we will walk together with you through the available labs we have. And of course, last but not least, there is the eBPF Summit. We are very proud to again be hosting the eBPF Summit end of September. It's basically our conference around everything related to eBPF. If you are interested in low-level eBPF, or if you're interested in how to use it in product, or how others are using it in products or technology, or of course how it's used in Cilium, join us for the summit. The agenda is already out, so feel free to register for the event. Check out the event agenda, what is interesting to you. And if you are lucky, then there is a watch party hosted in your city. We have 3 or 4 cities by now. We hope to get more cities where watch parties will be organized and where people interested in this can gather and, well, watch the event, watch all the tracks and so on. And with having said that, I think we're done for today. Thank you very much for all the questions. Thank you very much, of course, for the presentation, Philip. That was awesome. This will also be available later as a recorded stream. So if you want to share this with others, or if you want to go back into some of the topics, feel free to check out our webpage and then find it there. And with this, thank you very much, Philip. Thank you, everyone who participated. And I'd say goodbye. Take care, everyone.
Thank you for having me. Bye.